Alright, how you doing? Welcome back to the next video on the Soldier of Fortune 200 edition series. I'd like to apologise, first of all. It has been quite a while since I've done a video. Just to let you know, a few things happened in my life that I had to deal with, and I had to take some time out from the game to sort that out. But back now, got a little bit extra free time. I've done quite a bit of work since the last video, and I'll take you through what I've done and where we're at just now, okay? Excellent. So in the last video, I was attempting to convert this OpenSoF2MP game, which is based upon OpenJK, from 32-bit to 64-bit. Although that's not complete, I have pretty much done it. So that's where we're at just now. And I'll take you through the code and show you what I've done. So, in fact, I'll show you the game working first of all. So this is 64-bit. In fact, I'll show you 32-bit. There is one problem that you'll see in the UI that I haven't yet fixed, but that's the last error before the UI works, and I'll explain it all as we go. So make sure that breakpoints are on. And go. This is a 32-bit version. So there you go, the UI we all know and love. Everything's there. And there you go, so that's the 32-bit version. And this is the 64-bit version. As I say, there is one problem which you'll see when the game starts. So everything is working apart from the skin on the model. For some reason, if you look at his right leg there, there's teeth. So what's happening is the skin for the face has been applied to the body, and I can't for the life of me work out where that's happening. But I'll get it. It's just another. It's the last bug in the UI that I have to fix. So everything else works as it should. All the controls are there. Graphic options. Everything doing what it's supposed to do. I'll put the graphic things back to what it was. I'll take you through what I've done. This is actually a lot of work. This was really actually quite difficult, but I really enjoyed doing it. So, as I say, it's not complete, and the reason for that is there are OpenJK, the OpenSoF2 game uses a virtual machine, and the virtual machine runs pretty much everything in the game, the UI, the game, and the server. There's 3 separate components to the game, and the virtual machine code is complete. I'm fairly confident that that's working and that's complete. The UI code, if I go to CL_UI, there is a switch statement. A massive switch statement that controls everything. When the UI runs, anything that operates within the virtual machine is working, but it does system calls that are with the virtual machine, and all system calls go through this function CL_UI system calls, and it's a massive switch statement. So there are 3 switch statements like this, one in the UI, one for the game, and one for the server, and the one for the, apart from that, the skin not working on the model, the one for the UI is complete. And when you look at the ones for the game and the server, it's pretty much the same code. It should just be a matter of copy and paste. I haven't done that yet because I wanted to get this video out because it's been quite a while since I've done one. So I'll take you through the code changes that there have been. There's actually a pretty extensive changes to much of the code within the game, and the basic premise is this: to go from 32-bit to 64-bit, you double all memory sizes. That's the basic premise of the conversion. So we'll start in the virtual machine because that pretty much runs everything. So the stack size and local pool size are doubled. all memory sizes within the virtual machine are doubled. In the last video, I showed you how that I got the code to compile, and after that, what I did was I went through every file in the code and changed all integers that reference memory locations to longs, so 4 bytes to 8 bytes. So we'll start in the VM code with VM underscore create. This is where the virtual machine is created. After a couple of checks, it comes down and it loads what's called a QVM file. I think it's Quake Virtual Machine, which is a code file that tells the virtual machine how to make the UI, how to run the game, and how to run the server. So there's 3 QVM files in the game. One for the UI, one for the game, and one for the server. So the one I've been working on to get everything working is the one for the UI. So, well, that's loading the DLL if it's a server. So is this it? Load the image. Yeah, so the VM / the name of the file and then QVM. It gets the QVM file and it loads it into the position in memory referenced by header there. It then calculates all the different parameters, and it comes down to creating a section of memory that the virtual machine is going to use through all its operations. And this section of memory has 4 sections. It's got an initialized data section, a string data section, an uninitialized data section, and what they call a local pool. And a local pool is where all the operations are carried out. So the virtual machine memory is doubled in size to accommodate the change from 4 bytes to 8 bytes. This is the basic premise of the 32-bit to 64-bit conversion. So that means all integers become longs. Floats don't double in size, but what happens is you get a float and then you get 4 bytes after it that aren't used. So when you think about it, if you double the size of the database, all the original offsets will lie within the first half of the database because you've doubled the size. So the midpoint of the database is an important position, which I'll show you how that's used later on. Allocating the space and memory for the database. So every change, with the exception of changing integers to longs, every change I've made in the code, there's a comment convert to x64. So if you were to type that into the search function, you'd find all the changes that I've made. First of all, we copy the initialized data from the header file into the database, adding and doubling the size of all variables. All initialized data there's no double precision variables, and I don't think there's any longs. So everything is doubled in size. All 4-byte integers are doubled, and that doubles the size of the initialized data section. We then move on to the string data section, where all strings in this game are ANSI strings, where each character is referenced by a single byte, and they're all changed to wide car strings, where every character is referenced by 2 bytes using wide cars. So that's done simply by getting the length of the string and using MBS to WCS to double the length of the string. So what that means is, the way it's worked, if you double, there's a lot of things that went on, but basically all strings in the new database, the double database, are wide car strings, and all strings out with the database, which is only in the virtual machine, are ANSI strings. So what you have to do is you have to convert back and forward when referencing strings within the virtual machine database, and I'll show you how I did that very soon. So you come down here and then you compile the database, the virtual machine, and you do that in this function here, VM underscore compile. And what this does is it takes the code from the QVM file, looks at each opcode, and depending on what the opcode is, implements a particular string which represents opcodes for assembler, x86 assembler or x64 assembler in this occasion. So if it's 0, it doesn't do anything. If it's op break, it does CC, op enter. The original code here I've put as a comment. So the original code was to emit the string 81EE, which is sub this value from the ESI register, and that value is put in by the emit4 constant 4 function, and then break. So to convert to 64-bit, I've used the RDX register as a sort of general purpose register, and instead of subtracting a number directly from the RSI register as I did above, you move the value into the RDX register. You double the value in RDX, because remember, if you double the size, this is an important point, if you double the size of the database, then all offsets have to be doubled to reach the appropriate variable. So then you move the value, the offset into RDX, you double the value in RDX, and then you subtract that value from RSI. Moving on, basically all x86 assembler code has been converted to 64-bit assembler code, and the only change is that any offset that points to virtual machine memory is doubled, and that's basically it. This is not the original way I did it. There's actually been 3 incarnations of how I did this. First of all, I decided to double all values, and whether they were offsets or not, but what I found was I couldn't distinguish between values that were used as offsets and values that were just normal integers that were used in comparisons and jumps and that sort of thing. So then I decided to not double anything and only double it as it was used, and I got the same problem, not being able to determine what values were integers and what values are offsets. And eventually I came to the realization that the only time a value needs to be doubled is as it's used. And so what I've done here, is this it? Yes. So here we have the assembler, the x64 assembler operation, move the value in REX, move the Q-word value, the 8-byte value in REX, into the memory location referenced by RBX plus RDX. So RDX up here is the beginning of the database, and RBX is the offset into the database. And so there's 2 types of offsets. One that is calculated from the start of the database, as that one is, and one that's calculated from the end of the database. You get the end of the database and you subtract in. So every time an offset is used, if the offset points to the first half of the database less than the midpoint, then it's calculated using the from the start of the database, and if it points to a position after the midpoint, then it's subtracting from the end of the database, and that's how you determine which way to calculate it. And so if it's using the start of the database, you just double it, shift right RBX1, which is the same as multiply 2, and if it's subtracted in from the end of the database, you take the maximum size of the database, 800,000 in hex, move that into the R12 register, subtract the current offset, double the difference, and then subtract that new difference from 800,000 again, and that gives you your new offset. So you do that any time an offset is used, and that's basically, after much complicated nonsense, that's basically all you have to do to get access to the correct variables and the correct positions in memory while changing to 64-bit. So that's mostly the VM operation complete, but there was a couple of things that became apparent as I worked through it, and that is, one of them was string operations. If you double every offset, then you move forward 2 bytes, whereas before you would move forward 1. So if you're doing a string operation moving forward each car in the string, you would end up moving forward 2 bytes and missing every second car. That turned out to be a problem, and if you look, where is it? Where are we? I think that's it, yeah. So op_load1 is load 1 byte from a position in memory, and that's the one that's used for string operations. That is the original x86 code, and this is the 64-bit code where you've got the offset calculation there, and it's pretty much just a standard changed 32-bit registers into 64-bit registers apart from that. But this comment here is the original algorithm I had created, and it was getting very, very complex, because what I thought I had to do was take the value that the offset points to. First of all, work out whether it's a string. It might be an integer or not. If it is a string, work out what position you're in the string. Work out whether it's the start of the string or the end of the string, and then subtract the current number of bytes you are forward in the string from the current offset. And it was getting so complicated. But even if that's all it was, it wouldn't have been too bad. But what happens is you get multiple instances of op_load1 operating together. So one code would work with one instance but not the second one, and sometimes there's 3 instances. So I was getting a very, very complex algorithm that was just getting messy and messy and messier. And I thought to myself, there has to be an easier way to do it. And then I had a bit of a revelation. I realised that although the position in memory, the offset, if you double it, moves 2 bytes forward, it also reads 2 bytes forward each time, and it only reads a single byte. It doesn't read a word, it doesn't read 2 bytes. So although it writes, it separates the ANSI string into a wildcard string by putting a 1 byte gap after every character. It reads the same way. So as far as the code is concerned, it's reading an ANSI string, because it only reads every second byte. And when I realised that, I realised I didn't need that big, long, complicated algorithm, and just simply letting it run as normal would work, and it has. So that's string operations. What else is there? So I wasn't concentrating on what I was doing, and when I first started doing this, one of the things that I did was I doubled to get from 4 bytes to 8 bytes. I made all floats into double precision numbers, and I didn't realise at the time that's not a valid conversion, because floats and doubles are stored in different formats. So if you take the value that's in a float and put it in a double, you're changing the numerical value of that variable. So that became a bit of a problem. I looked at trying to convert from float to double every time it's used, and then double back to float, but that was getting complicated. And then I realised there was actually no doubles used in the game as far as I could tell. They were all floats. And so I just used the same code as before. I didn't change it. Apart from using RDI instead of EDI to reference memory offsets, it's exactly the same code, and it just uses D-words. It works with D-words, 4 byte integers, 4 byte floats, instead of 8 bytes. So all the floating point operations, assembly operations, are pretty much the same as what they were. So basically, rewriting the assembler code for the virtual machine basically came down to understanding that doubling the offsets, doubling the size of the database and the size of each variable means that all offsets are doubled, and having to change and check each offset to make sure it's pointing at the right variable. And that's what it came down to, and that's what I've done here. So that is the virtual machine assembler code working correctly now for 64-bit operation. See if there's anything else. So we'll stick with VM_x86. One of the other problems with x64 operation is there's no inline assembler allowed. That is not supported in 64-bit operation architecture, and there was inline assembler used in the original game, in the 32-bit game. So what inline assembler just means, instead of calling out to a function, moving to a different part of the code, it just writes the assembler on the next line in the code, as if there was no function called to another position in the code. So what I did is I took all the assembler and I put it into, I showed you this in the last video, but I put it into assembler functions. And I've rewritten this assembler code. It got very, very messy at first, actually. There's no push add and pop add function in 64-bit, which is a bit strange. You would have thought they would have had that function in it, but they don't. So I had to write functions for that. I had to do a lot of different assembler functions to do different things, and they got very, very messy. A lot of this code isn't actually used anymore because I haven't deleted anything. I don't delete code until I'm absolutely certain I'm not going to use it. So where is ASM call 4? ASM call prologue. ASM call. That's not. Oh, it's down the bottom. There's ASM call 4. So this is the main bit of code that calls the virtual machine. The original code is commented out there, so that's the original code from there to there. And it wasn't going to be just a case of changing EAX to REX because there's no inline assembler and there's no what they call a naked function. In a naked function, when a function is called, the first thing it does is the epilogue and prologue, which is to set up the stack to be ready to prepare it for local variables and that sort of thing, to take the stack pointer RSP, put it into RBP, so you've got a copy of the stack pointer and RBP for that function. And a naked function, which is what you would generally use with inline assembler, doesn't do the function epilogue and prologue. So the first thing I did in this file to make it the same as the original code is remove the function prologue. So the function prologue is, what would it be? Push RBP onto the stack, copy RSP into RBP, and you reverse that operation with pop RBP. Then, because you've called a function, you've got a return value, you would move that into a position in memory, and then you take RCX. In 64-bit operation, the first parameter of a function is passed into the RCX variable, not onto the stack, as it is in x86. So you move, because RCX is used in the virtual machine, I copy the address, the value in RCX, which is the address of an array of 8-byte longs, I'll explain that in a second, into R13. R13 is not used in the VM, so it will be preserved through the call to the compiled code of the virtual machine. So, as I say, it got very, very messy. The first attempts at this, there was lots of different variables that I had to store, and at one point I think I was trying to save 15 different variables going into a function, and then I had the idea, instead of starting to save all these variables, create an array of long longs, 8-byte long longs, and just pass the address as the first parameter. So all these assembler functions now only have one parameter, which is an RCX, and any variable that I want to store is moved into this LILNGR ASM vars array, which has got 64 elements. Where is it again? Where is it? So this is it here. Most of these aren't used anymore because I've changed the code so much. There's only about maybe 8 elements of it used, but that is a lot of the stuff that I was passing in originally just to get it all to work. But as I say, most of that's gone now. It definitely doesn't need to be 64 elements anymore. So ASM call 4 does pretty much, I wanted the code that I wrote to be pretty much as close to the original code as possible to make the operation exactly the same, and it pretty much does exactly the same thing, which is, for what I've added on here, calculate the size of the locals to be added, which it does. That's not used. Oh, I don't do stack alignment anymore. So implement above x86 code. So that code there where it calls the virtual machine compiled code is pretty much exactly the same. There's two exit points that return there, and if it goes into the virtual machine, that's where it goes there. But if it wants to do a system call in that switch statement there, it comes out here and goes that way. And so that's pretty much exactly the same. So I'll come out of the assembler just now. There are two other functions that were important within the virtual machine calling the compiled code. Where is the first one? The first one is ASM call, which is actually the function you call to go into the virtual machine. And here are the parameters that you pass that are used within the virtual machine passed into that array. That's the call into the compiled code, and that's the returning of the parameters, which is pretty much exactly the same as what the original code did. One of the problems you have with inline assembler is the compiler doesn't seem to be aware that it's using inline assembler. So if you change the stack with inline assembler, the compiler won't see that, and it will try and access variables in the stack in the wrong position. So what the first thing I had to do was, for going into the compiled code, there's no change in the stack. That function there is in essence naked, the same as the x86 version. But to access variables that would have been created by the compiler after coming out that function, I had to realign the stack. And also I had to realign the stack for, what was it? Oh, what is that? XMM operations, which is floating point operations using the XMM series of registers, which have to be aligned on a 16-bit boundary, which is what that align stack does there. So it aligns the stack. You go into the system call switch statement with that. You run your system your system call. You come back out. You unalign the stack. You pass variables to where they need to be, and that's the end of that particular call into the compiled code. So one of the problems I had, because we're using my own assembler, is in debug it compiles it slightly differently. So this if debug here, the value in RDI which is used by the virtual machine is lost if you're in debug mode, because it's copied out from another value. So this function there just restores that value, and what it does is ASM restore RDI. Is that down the bottom, I think? I hope this isn't too confusing. It's a lot of work, and it took me quite a long time to do this. ASM align, where is it? Restore RDI, is it? Have I done it somewhere else? Yeah, I don't know what that is. Anyway, so all it does is it pushes the original RDI value into position in the stack that overwrites the original position, so it overwrites with the correct value. And then you return it there. Down at the bottom, you have VM_call compiled, which is the function above ASM call, or is it the other way around? Anyway, they're both used for calling the compiled code in the virtual machine, and all the values here that represent memory locations are changed to longs. Here we do the calculation of the program stack value because the virtual machine memory space is doubled, remember? That's the original code for passing in the current arguments to that call to the virtual machine code. Changed to x86, all the positions are doubled, and all the arguments are longs instead of integers. And then we set up the parameters for the function call, and we push in, we head in and call the function. And my own ASM push add and pop add function, because as I say, x86 doesn't have a push add and pop add. So there is one thing I haven't done yet, and it might be a bit of a problem. I was going to talk about this in the end, but I'll just talk about it now while I'm here. I have literally zero experience of Linux, and that's, although I'm quite good with assembler, that's AT&T syntax, which I've never done before. So it should just be a matter of copying and pasting the assembler I've written in the x86 syntax in there and running that, but I have zero experience on Linux. I don't have Linux, although I could easily download it and try it. I don't know what I'm going to do with the Linux stuff. I do want to get it done and have it working and fully working in 64-bit, but I'm going to have to wait and see how that goes. Anyway, so that's that. So that's the virtual machine assembler code. We've talked about inline assembler, the virtual machine, talked about the virtual machine. So the system calls that run for the UI pretty much all access virtual machine memory. Now, because we've doubled the size of virtual machine memory and doubled the size of all variables, all offsets are moved forward. They're all doubled in length and position. So all these system calls then access the wrong position in memory, and that had to be fixed. So with the very simplest terms here, com memset, which sets a particular portion of memory to 0, is doubled in the size of memory it sets. You double memcopy as well, and I'll take you through each of the system calls, or a few examples of them, and show you what I did to get it to work. And so the basic idea is this: in the virtual machine, all memory positions are doubled, and in non-virtual machine memory, everything is exactly as it was before, so all offsets are not doubled. So you have to, and it only happens within these switch statements. So all other code out with the switch statements should work as is, apart from, I'll show you a few of the things that had to change, but most of the changes and most of the things you have to concern yourself with happen in these switch statements. So string copy. Remember, all strings in the virtual machine memory space are now wildcard strings, and all strings in all other parts of the code are ANSI strings. So string copy, virtual machine to virtual machine. VMA is get a position in memory within the virtual machine. So it's wildcard, and you're copying from virtual machine memory to virtual machine memory, so you just do wildcard string copy. VMF is get a position, a float that's stored in virtual machine memory, and all that had to do there, floats are 4 bytes. To get them all 8 bytes, you just multiply the value by 2, and that works. So what have I done here? What can I show you? Quite a lot of the functions have to have two types of variations. One is DBL, which is just doubled. Positions in memory are doubled. And I'll show you this. So set color sets a position in memory to reference a particular color. So the original set color function takes an RGBA value, does a couple of tests. Don't worry about command buffer. If RGB is not set, it creates a new float with the values 1111. So 111 is RGB, which is white, and the alpha channel is 1, so it's fully not transparent. And you take the values in RGB, each float, because it's an array of 4 floats, and you pass them into that array of 4 floats there, and that's then used. That's the original code. In the doubled version, because we've doubled the positions in memory, you then have an 8-byte. What has to happen, in fact I can show you, this is a bit, what's the best bit to show you? Where is, yes, okay, go to definition. So any struct, any data format that's stored in virtual machine memory has to be doubled. But it's not just a case of doubling each variable in size. What had to happen is, depending on the type of variable, you had to double it in a certain way. So you have these variables, a vec underscore t is a vector which is a float, 4 bytes in value, 4 bytes in length. Vec3 underscore t, which is an array of 3 of these. So vec dbl underscore t is also a float, but instead of doubling the length of the individual variables, you double the number of variables. So vec3 dbl underscore t has 6 floats instead of 3. And the way you access it, if you imagine the offset being doubled, you'd have the first float, which is accessed, the next float is not accessed, the next one would be it's every second one that is accessed. And so when you go and use this, implement this in the code, only if it's virtual machine memory, remember all other sections of code are just normal. Command is a local variable, so it's set up in the stack, so it's not in the virtual machine, but it's having variable values from the virtual machine memory copied in, so it's every second array element, every second float is copied in. And so if you create a new one, it's every second one is not used, and every one, so it's 0, 2, 4 and 6 are used, and the other ones are zeros and not used, because you double the offsets. So that's what you do with floats. Whereas, let me get you a struct. Can I use that one? Yeah. So the original struct has a handle called cvar handle underscore t, an integer, a float, an integer, and a char array. If you're going to double those variables, you don't double a handle because it's 4 bytes originally and 8 bytes automatically. If we go to there, it's not the right one, but I changed that to long there. So anything that's a handle to a file or handle to a memory position is changed to long. So modification count was an integer, it's long, so that's doubling it. What you have to do with floats is you can't change them to double as I did originally. You have the original value which doesn't change, and then afterwards you just put in another float, and I've called that do not use. So you see the name of the variable you do not use, and that pushes the next variable forward by the correct amount of bytes. Long integer is a long, and char arrays, you just double the size of them. It's double the amount of bytes in them, and because they're going to store wide chars, remember, not ANSI strings. So you do that with all the different types of structs that are held in only within virtual machine memory. So you don't change the original struct because that will be used in other parts of the code. You create a new struct named DBL and you use that only in virtual machine code. So where are we? So any struct that is VMA, which means it's held within virtual machine memory, has to be doubled. And I've shown you about the DBL functions. The second type of change that had to be made for these function calls is wide char, and it's basically whenever it uses a string. So the original function cvar register had a what was in here? 2 constant char variables, and in order to accommodate the fact that a wide char, you just change them to wide w char underscore t, and wherever there's 2 ways to achieve it. One is, what have I done here? Yes, so it's pointing to a location within virtual machine memory, var name and default value, so they're already wide char. So you use WCS length to get the length of them. You allocate a section of memory of that length, and you use WCS TOMBS, so wide char string to multi-byte string. Multi-byte string is what you call an ANSI string, and you copy that string, you convert that string to an ANSI string in that position in memory, and that string is what you pass in to the cvar get function. So if you go to the switch statement, wherever a constant W char is used, or wherever a constant char was originally used, if it's virtual machine memory, it's going to be wide char. You just convert them, you allocate space, and you convert them to ANSI strings, and you pass the ANSI strings into the system call function, and then you make sure you clear it at the end. So I was going to say with wide char there, where are we? Where is it? Oh no, that's not the correct function. I think that's one. So one example here, this is slightly different from the example that I just shown, in that it does have a wide char string that's within virtual machine memory, but it's a buffer. It's not passing in a string the buffer is going to be written to, and it's in virtual machine memory. So in that situation, where are we? Instead of using the strncpyz copy function, it's mbs to wcs, multi-byte string to wide char string. So basically, copying a string to virtual machine memory needs to become wide char, and retrieving a string from virtual machine memory needs to be changed to multi-byte string to ANSI string. So, what else? I think that should be pretty much it. Anything, as I say, anything that's a string in virtual machine memory is wide char. You just convert it to ANSI string and pass it in as normal. Here's another struct I can use as an example, see if there's anything that's a bit bigger. So, ref entity type, I think, is an enum. Yeah, it's an enum. So an enum is just an integer. It's an integer, so in that situation you can't double the length of an enum, so you just do as before, create an exact a variable of the same type and just call do not use. Q handles are changed from ints to longs, same as file handles and SFX handles and clip handles. Pointers are automatically changed from 4 bytes to 8 bytes, so you don't have to create anything after them. There's your vector 3 doubled 6 element vector 3 arrays instead of 3 elements. Q booleans are, I think they're 4 bytes, so you do the same as before, same as with floats, and that's pretty much it. Arrays of bytes, there's different ways you can do that. And what I find was you double, if there's a multi-dimensional array, you double the number of bytes in the second element, and that doubles the total number of bytes. And so you access the first index as normal, and every second value, every second element in the second index. It really got quite complicated, but as I say, it's only to do with it's only within the virtual machine because we've doubled that. Memory size to accommodate larger variables. The reason for this is the QVM files. We weren't given the original source code for the QVM files. They come with the. They didn't actually come with the source code. They're a part of the game files in the base directory. So I looked into decompiling them and then recompiling them 64-bit, but I didn't get anywhere with that. So the code I've written is actually an interface, a 64-bit interface to the 32-bit QVM file. So it accommodates the 32-bit QVM file and converts it on the fly to 64-bit. And as I showed you, the game's working, so everything's working, so it's good. So I'll show you quickly sv_game, is it? I haven't done the switch statements in the server or the game, but as I see there's the server one. It's pretty much the same code, or at least the same type of conversion. I'm not expecting anything different. So there's a VMA queue time. A queue time I've already done, I think. Well, that's the original one. There's queue double. So it shouldn't. It will probably be a little bit time consuming, but it shouldn't be too. It shouldn't be too difficult to do the game and the server stuff. So what else is there? I think that could be us for the game. I know I'm going to close it all down and go away and realise there was other stuff I wanted to talk about. Let me think. Let's have a look. There's a lot of little things that had to be updated. One of the MP3, I think, is in here. Yeah, so that code there is right linear blast stereo 16 had to be rewritten in 64-bit. It wasn't too difficult, just RDI instead of EDI. But in that situation, because what you got to remember, although the architecture's changing, all the values used in the game are still the same. So they're still 4-byte floats they're passing in, even though it's going into an 8-byte register now. So what else? I think that could be us. I know I'm going to realise there's other stuff that I want to talk about, but that could be us. So what I'm going to do with this, I'm going to get it finished, do the game. Once I get that bug fixed with the skin and the model, I'll then do the server and the game switch statements, and that should be it working completely. As I said, the Linux stuff I'm going to look at later, and then just going to test it all to find any remaining bugs, get it fixed. And what I'll do is I'll put the source code on my GitHub page as a fork of the guy who did it originally. As you can see, the way the guy describes it, he says OpenSoF2MP is an attempt to create Soft 2 using the OpenJK source code, but he says it's heavily modified, and it is heavily modified, but all the files are there. So although it's not OpenJK, it is still the same original code. What else? I think that could be us. I don't think there's anything else. Okay, so I hear you saying, why are you doing this? What's the point? So by converting OpenJK to 64-bit, it's not OpenJK, OpenSoF2MP to 64-bit, what you can do is, and I've already done this because it took ages, you can open up a new C++ project in Unreal Engine. You can copy the OpenSoF2MP project into the into the Unreal Engine project folder. You can go into the Solution Explorer of, I called my Unreal Engine project OpenSoF2 test, and you can open two files. First of all, you need to go into Solution Explorer, right click in Games, and add existing project, and you do that twice. Once for Soft2MP and once for RD Vanilla. You add the file soft2mp.vcproj, which is in the code MP folder, and the RD Vanilla vcproj file is in the RD Vanilla folder. You then right click on Soft2MP, go to Build Dependencies, Project Dependencies, and you click RD Vanilla. You then go to OpenSoF2 Test, Build Dependencies, Project Dependencies, click on tick the box for Soft2MP, and what that means is whenever you build OpenSoft2 test, it will first of all build RD Vanilla and then build Soft2MP, so they'll automatically build when you build that. One thing you also need to do, right click on OpenSoft2MP, go to Properties, VC++ directories, and in external include directories, I've added the code MP folder for Soft2MP. So all the include files for that game are then included in the Unreal Engine project. And what you then do, you open up the first person character CPP file, and you add an include for engine / engine.h. You come down to the function begin play. Just at the end of that function, you include qcommon_q_share.h, which is a file from the Soft2MP. You create an f string using client_window_title, which is a define from Soft2MP, and then you use the gengine adds on-screen debug message to put that client window title message on the screen when you start the Unreal Engine project. You build it, and it takes quite a while to build because I think there's 4 projects that have to be built. And what happens is, and this better work, that's the project. I've already built it. I know it's working. I hit Alt P. It starts. Oh, okay, I'll do it this way. Play Soft2_MP. That string comes from the OpenSoft2 project, not the Unreal Engine project. So all the code from the OpenSoft2MP project is now fully available to your Unreal Engine project in 16-bit format, because you can't mix 32-bit and 64-bit projects. So there you go. That's the point of doing it. So one thing, what I'm going to do with Soldier of Fortune 2 Unreal Edition is to take OpenSoft2MP, or to take Soldier of Fortune 2, the original game, and have it as a mod. I'm going to do all sorts of things like ray tracing and all that sort of stuff to it as well. I'm going to do that in the background. And now I'm going to get on. So I watched a video on YouTube about the guy, what was the No Clip Documentaries, gay video game documentaries, and there was a guy who made a game called Choo Choo Charles, and one thing he did was he made a trailer for the game and put it on YouTube, and he got a lot of attention. But what he did was he built the game engine first. The trailer he put on was pretty much done. The game was pretty much done. They just needed a few things added and that sort of thing. I made the mistake of announcing this project before I'd even started coding. I realised that was a mistake. Now, I should have built the game engine and then announced the project with a trailer of actual gameplay. So I apologise for that. I apologise there's not been a video for over a year. Life has been absolutely hectic, and this has taken 8 months to do. But I'm happy to say, not quite complete, but it's just copy and paste from here on in. OpenSoft2 built on OpenJK is now 64-bit in Windows, and I will get a Linux part of it done as well. So I am now going to go away and build this game engine. I'm not going to do too many videos. I'm not going to do a video a month anymore, because that just put me under pressure to have something to show you. I'm going to go away and build this game engine now. I've got Unreal Engine 5.3 downloaded on my desktop, and I've started building the first map. What I've decided to do, I'm not going to recreate the maps in Unreal Engine. I want to create new maps. So what I've decided to do, for every map type, I'm going to create one map. So there was 2 Prague maps. I'm starting off with Prague. There was 2 Prague maps in the original game, Prague Streets and Prague Streets Siege. I'm creating one big map that's going to be Prague Streets, and I've only just started, but it's coming along. So I'm going to create one airport map, one Hong Kong map, one Prague map, one Jordan map, one shop map, and then once I've done a map for all the original game types, I'll then think about creating my own maps for it as well. It will take a while, but we'll get there, don't worry. So I'm going to go away and build this game engine now, and I'm going to start with my Prague map And once I've got the prag map the way I want it to be, I'll then build all the game components, all the functionality of the game, and the last thing I'll do will be netcode, I think. So anyway, OpenSoF2MP, OpenJK 64-bit. I think that's everything I want to show you. There's probably a lot of stuff that I thought about before I wanted to say that I haven't shown you, but that's just going to have to be the way it is. That really was difficult to do, but I'm glad it's done. So, I hope you enjoyed that. I hope it was informative. I want you to know this project is moving forward. I'm going to go away and build the game engine now. I apologise for not having a video for a year, but we're going to get it done. Okay? So, thank you for watching. I hope you enjoyed that. Until next time, see you later.